only. I think Varun is there. We'll wait for some more time.
Sir, I actually came across some questions in organic chemistry, sir.
Yes,
Actually, I'm going to some another. I'm going to another coaching, and then those tests that they kept, I couldn't like really figure out like the mechanism of how they got the final product.
Okay, do you have the question with you?
Sir, can you send a photo in the WhatsApp group?
Yeah. Just send me personally. Like, do not put it in the group. Put it to my number.
Okay.
Yeah. Is it sent?
Sir, I sent some photo.
Yeah. Okay, so first one is this with H2SO4. Okay. Right. So the first question is, I have what? Yeah, I have a methyl group and OH, and I have one here bonds with this. I go for H2SO4 bar heating. Right. So this is my dehydration reaction. Maybe 1 second. I think you will not be able to see. 1 second, guys. Okay. So I think now you're able to see. Right. So this is the question that was given to me. Right. So obviously you see alcohol with H2SO4 is gonna give dehydration reaction, right? So if I do it, so maybe first the H plus from this attacks the lone pair on oxygen, so you'll form one CH3 and one OH2 plus, then this, the methyl group. And obviously now the methyl group, I mean the H2O leaves, minus H2O, CH3 with a carbocation on this carbon. There is a double bond, and this, right? Okay, now the next step can be, say this is an allyl carbocation, right? I cannot make a double bond. See, I cannot remove, basically, I cannot remove this hydrogen. This cannot be removed, right? What I can remove is maybe this hydrogen, but I don't think that is going to be. I'll look at the choices. One second. So definitely some tautomerism kind of stuff is going to happen, no doubt about it. Okay, right. So there is a carbocation, and if it undergoes some kind of rearrangement, say this comes here, what will I have? B. No, there is a double bond here and a positive charge with another double bond here and a methyl group. Right. Okay. Now I cannot do anything else other than this, I
Yeah, I
guess.
did up to this step, sir.
Okay, you did up to this step. Okay, fine. Or is there something else? They're giving phenol, so somehow I should get this is already an enol, right? If this is already an enol, if I can write it like this, 1CH3, and this was the enol. Say now, if I make it as a double bond O cannot come.
Sir, can the double bond thing take place in resonance, sir?
That's
Something
what.
like
That's
that.
what. Say now this comes here. No, it cannot happen like that. No. Okay, let me check. Uh-huh. Say if that goes here again, the same thing only will come. It's not going to be much deal. What's happening? Let's see. Oh, can I have acid catalyzed aldol condensation? It is very much possible. But again, there are no alpha hydrogen which can remove, so that is out of the picture. Mm, minus, and obviously there is no other bond I can break. There's no other way. Dehydration can also happen. Or if there is anything else I can remove, if the carbocation was here, then also there is no possibility. It has something to do with tautomerism. I'm not getting it. How will I bring in tautomerism here? So if it's an enol directly, if I have this, I will be forming CH3, COH, double bond CH2. Right? This would have been the case. But this is not the case here. minus. And what will I do with this carbon? And sodium sulfate. It is. Or if I go by the thing, say I say that this is assuming like this is H3O bar H plus, right? This is like an this thing. So if H plus, if I'm going to form a carbocation, this is where I'll form the carbocation. This bond will be broken. Forming one more OH doesn't make sense. H plus attacking here. I mean H plus attacking here. I'll get a carbon.
Like the can like H plus attack the double bond also, something like that.
Possible. It's not like we cannot avoid it. But even if that happens, actually, if this attacks here, OH, now I'll have double bond OH plus, right? Now there is another this thing. Now say, there is a double bond here, here. Now what I can form is, no. Okay, now if this attacks, obviously for removing the,
Sir, then a positive charge will be formed on it, and then after that you can break the double bond.
yeah, that's
So it
what,
becomes
like you have
single
to
bond over
break
it.
the double bond. If this double
Then
bond
it becomes single
breaks,
bond over plus.
wait. So there is a double bond. So what happened? I had a double bond here. Now this will come here and this will go here. And what will I form is CH3 OH, double bond here, and there is a OH here, and now the double bond is there, another CH3. Right now, this is an enol. Now, if I go for the keto form, this is the enol form. If I go for the keto form, I have CH3. Say this will become. How will it become double? This is an enol. Say now if this was O minus, this will come here, this will go back again here. I'm going to do the same thing. No. What am I doing wrong? Okay, or if I make this come here, are they having all secondaries? Okay. This doesn't seem to be some tough question and all, but we are doing something fundamentally wrong. That's where we are trying. Okay, let me write it again. Okay. Now, the possible places where the H plus can attack is either this oxygen. Oh, wait, I have to show you. Yeah. So the possible places where the H plus can attack is this oxygen, or say one of the double bonds, or say this one. Right. We tried with H plus attacking here. I'll form a carbocation here, and this will come. And then what will happen? There will be a carbocation here. And let me try this way. A carbocation here, a H plus going from that. If I just make it directly H2, H plus is attacking here. And if I make it like this is double bond CH2, this, and this. That should be one of the possible products. H plus moving from that. Right? Or if a carbocation is formed here, what can happen? No. It's attacking here. Oxygen will have a positive charge. Oh, wait 1 second. So let me attack the H plus here and check. Last time we did something wrong. Okay, so this given CH3 OH double bond, O double bond OH plus. Now what can happen is this bond can come here and this bond can break. Okay, so next CH3OH, a double bond and a OH and a double bond CH3, right? Okay, now this can undergo tautomerism. If this undergoes tautomerism, I'll be ending up with CH3 OH, one double bond, one double bond. Oh, no. Wait. Let me have this only. Okay. So now say another mole of H plus comes and attacks here. I remove this. So I'll become OH2 plus. And I can remove this H plus, which means that I can remove the hydrogen. Beta hydrogen can be removed from this. Right. So I can end up with one CH3, one double bond here, another double bond with OH, another thing with CH3. And now this can undergo tautomerism. Do I have to make another tautomerism? Carbocation and this hydrogen would be going. But in the this thing, there is no I can directly write it, right? So if I write it properly in the form of benzene ring, I'll have one CH3 here, another CH3 here with OH. Yes. So this would be the answer. So any answer is matching. Let me check. One CH3. So if I write it properly, whatever how they wrote, one OH and then one carbon atom away, another one, and this side two carbon atoms away, another OH, I mean another CH3. So any answers matching? Or they have two OH. How is it possible? None of the answers are matching. What is wrong? This time we did correctly only. This happened. I mean, okay, first I formed the H plus attacking here and this bond coming here and this goes here. So this is done. So I'll make a double bond here with an OH. And then what I did. And then I attacked H plus here. So I made the double bond here. But if this is correct, they are going for one more OH, which is where? Or if I stop with this only, but there is no double bond. Oh my God.
Sir, they gave the answer as the one and the D option.
One in the D option. Okay, D is two OH groups with two methyl groups. Okay. No. Something is happening. Okay, I think I have to sit and work with this. There is something we are doing wrong.
Okay, sir.
Or wait, let me at least work it on 2 more minutes. If I'm not getting, I will work it on later. Okay, give me 2 more minutes. You can also try. Everybody, I mean, everybody. Again, I showed you the question. There was an OH, this thing, and they are putting concentrated H2SO4 and heating. And he's telling, you can send it in your group. You can send it in the group also if you want. Let them see. How to OH. So they're telling none of them is getting eliminated. That's what they're telling. Is that what they're telling? Or one eliminates again it forms. One last try.
Even when I saw the question, I thought that it won't be.
Yeah. No, that's what happens in organic. Question seems very simple, but there's a small thing we are missing out somewhere, and that is what is creating all the problems. And what I understand is when the CH3, I mean, the carbon is having CH3 and OH, both of them are moving. So definitely that has to go, right? So let me put it back to these. If I form the carbon, this and this and this, okay. So that is gone. And oops, let me make the first step. Is not going to be there. One last, right? Which plus, so this will come, this will break. So if that happens, CH3OH with a positive charge. One OH. Okay. Now say if I do methyl shift. I will have OH with a positive charge, CH3, this, and this. And then stay here. Okay, I almost got it. If there is a hydrogen here, and if I eliminate that from this, OH, double bond, CH3, CH3, one OH, and there is double bond. Is this the answer? One here, one here. Okay, guys, I got it. Okay, so this is what happened. Okay. So what happened is I just made the H plus attack this thing only. Okay. Now you'll form OH plus. So obviously to compensating this bond will come here, make a double bond, and this bond will break. This is what we did last time. But what we missed last time is that this carbon atom is going to have a positive charge, isn't it? Now this is a secondary carbocation. I can do methyl shift. This CH3 comes here, so you'll form this, right? Now you have OH here. Then I have another hydrogen here. Now that will be removed minus H plus to form this compound. Yes, it is the answer. Yes, Varun, got it?
Yes, sir.
Okay.
Thank you.
Okay. Is there any other question there?
Sir, can you check the 15th question, sir?
15.
Mm.
12, 14, 15.
Only do the reaction in the first question, sir. Like the other two, it's okay.
Okay. So 15th is that aldol. I mean that CH3CHCH. That question.
Yes, sir.
Okay. Fine. What is this? Oh, they are telling when I make this undergo heating. No, what are they asking? They have given the choices only. Where is the question? The question is up. Oh, okay. Which of the following would yield a racemic mixture? Okay, fine. Racemic mixture. Okay, Br2 in the presence of CCl4. Bisulfonyl compound getting heated will form a double bond here. That will not be racemic mixture. That will be actually. So the thing is, if I look at A, right? So A, one SO3H, and this one another SO3H. Now, if I heat it, I will remove this, and I'll remove this, and by resonance structure, you will be getting a compound like this. Right. So I'll be getting a compound like this. But this will be optically active. I mean, this is optically active, but this will not be optically active. So A cannot be the answer. Okay. Now, next question. In case of this, if I add NaOH, I will be forming this particular compound. Right. So I will have CH3. Oh, we are not able to see. I'm sorry. I'm not even writing it. Okay. Sorry, guys. Right. So when you hit the option A, if you check, right now, this is optically active. Right. This is optically active, and this is not even optically active. And then only I can speak about racemic mixture. Okay. So A is not the answer. Right. So then what they say is I have this particular compound. CHO, and this is reacting with NaOH, and that would be my aldol reaction, right? Now aldol, so obviously first it would be removal of this H plus, and then making it attack. Okay, now yes, in this case I'm going to get a racemic mixture. I'll tell you how. See, when you have a C double bond O, right? Now you can easily, or if I write it like this, if I have a C double bond O like this, right? Now any nucleophile for that matter can either come from the bottom or it can come from the top. Okay, or it can come from the bottom or it can come from the top, right? So obviously it is going to give me a racemic mixture, right? So B, according to me, will be the answer. Is B the answer, Kana? What did they give for this 15th question? Varun?
Sir, 1 minute.
Yeah. Okay, half an hour got wasted, but it's not a waste time. It's good. We worked on something.
Yes, sir.
B is the answer. Okay, good. It's easy. Like any, not only for aldol, any nucleophilic addition reaction, right? And okay, obviously it should be given that these two groups are not going to be that different. Only then it's fine, right? But still, in general, any carbonyl compound undergoing a nucleophilic addition will generally form a racemic mixture because the nucleophile attack from this side or this side, there is no restriction. So both of them will form in equal amounts. So it will form a racemic mixture. That's it. Okay, right, cool. Fine. So we completed aldol reactions. We completed the Cannizzaro. We looked at the mechanism. We looked at everything, right? So let us now go to carboxylic acid and its derivatives and amines. Okay, and with that, your organic will be over, and we'll do some problems. Maybe I'll take maybe for this one class, next class, maybe half the class of next for completing organic. Okay, fine. So going to carboxylic acids, right? So we know how to form carboxylic acids,
Sir,
right?
Sir.
Yeah, yeah.
Sir, can I quickly teach Clemenson's and Wolff-Kishner reduction?
Yesterday itself we saw, no?
Yes, sir, we did, but then...
No issues. So when I go for Clemenson's, right? So you have a C double bond O, and you go for zinc amalgam in the presence of HCl, right? So you will be ending up with CH2, this thing. So this entire double bond to oxygen is replaced with CH2, right? And if it's going to be for Wolff-Kishner, right? So there's C double bond O. I'll have to go for hydrazine in the presence of NaOH, right? Now you'll form again same thing, this and this. Okay.
So only the reagents differ, sir.
Yeah. So like there are conditions. For example, right? For example, what you have to understand is, say for example, in this, I'll take an example like this. I have CH3 OH, C double bond O, CH3. Sorry, CH2OH. Okay, if I have this reaction and I make Clemenson's product HCl, maybe you'll get whatever you want, but you'll have some side reactions also. The side reaction would be this Cl by this replacing OH, right? So at that time, going for Wolff-Kishner would be better. Are you understanding what I'm saying?
Sir. Yes, sir. Yes, sir. Yes, sir.
Right. Same way, if at all I have any acidic hydrogen, for example, if I had something like how to put it? Say if I have CH2, say again, this can also undergo nucleophilic substitution. Say for example, if I have Cl, and in this case, if I go for this, again the OH minus can replace this, so it is better to go for Clemenson's reaction, right? But again, you don't have to worry about all these, right? Both of them will give me the same product, but depending on what other functional groups are there in the particular compound, I'll either go for this or this, depending on the other functional groups. That's what will happen, right?
Okay, sir. Thanks.
Okay, right, fine. So now we'll go for carboxylic acids. Okay. Right. So if I look at carboxylic acid, how they are prepared, one preparative method would be definitely by oxidation, isn't it? By oxidation of primary alcohols or aldehydes. Again, we know if I have to directly convert primary alcohols to acids, I have to use a strong oxidizing agent. And for aldehydes, even if you use a mild oxidizing agent, it is going to be okay for me, right? That is one thing, right? And you've already seen one reaction. If I have, okay, you tell me, if I have an alkene, how will I form acid? What reagent can I use? I have to form COOH somehow, right? Whatever it is, tell me what reagent can you use here?
Sir, get a Markovnikov product, then do
No, one step.
KCN, then H plus. Oh,
I understand. That is correct. One reagent which will be able to do this. Or if I give you a specific reaction, if I had CH2, double bond CH2, and if I make one thing, I'll be getting 2 moles of HCOOH. What is the reagent?
Jones.
Sorry? Jones reagent. Jones reagent will not be able to do this. Jones reagent is CrO3 in H2CrO4. That is an oxidizing agent, but not capable enough to do this. What I have to use here? Okay, it's related to ozonolysis, but not ozonolysis.
for O3, sir.
That's what it's related to ozonolysis, but not ozonolysis.
Sir, ammonolysis, that process, is it that?
Okay, see, remember I told you there is one reaction which is going to behave similarly for, I mean, with respect to your ozonolysis, and that would be hot, concentrated, acidic KMNO4. Did I tell you? Right. So if it was ozonolysis, what would have done? Basically, you would have broken this and put oxygen, like put oxygen on both sides. Right. Now, what will you form is HCHO, 2 moles of HCHO. But since it is a strong oxidizing agent, this will be oxidized to acid. Right. So I hope you remember we did this. Okay. If I go for hot, concentrated acidic KMNO4, right, what you have to do is exactly do ozonolysis. If you form an aldehyde, convert it into acid. If you have a ketone, just keep it as such. Okay, now this reaction is capable of doing that. All right, this reagent is capable of doing this, converting alkenes directly into carboxylic acids. Okay, right. And then I can go for and this and all our normal things, oxidation of alcohols. We saw everything we saw. And obviously, you can go for hydrolysis of any acid derivative. Okay, we'll study about acid derivatives, right? Hydrolysis of any acid derivative, RCOZ. The Z can be Cl, Z can be NH2, Z can be OR, right? So now if you go for hydrolysis, H3O plus, right, you will easily form RCOOH, right? So hydrolysis of any of the acid derivative will give me acid, right? Say esters, amides, acid chlorides, cyanides. Even remember, cyanides, you might not understand that it is an acid derivative, but it is an acid derivative. I'll tell you how, right? So please understand this. If I have RCONH2, right? Now, when I heat this compound, what is going to happen? NH2, right? What is going to happen is I am going to remove H2O, right? If I heat this compound or if I use any dehydrating agent, obviously, right? So you will be ending up with RCN, and obviously RCN on hydrolysis first will give this, and this on hydrolysis again will give RCOH. Okay, right? So cyanides are also going to be one of the acid derivatives, but not directly. but still, just on hydrolysis first step, it will give me the amide, and then it is going to give the acid on hydrolysis again, right? Okay, that is one. So yeah, these are the different methods of preparation of carboxylic acids. Okay, fine. We'll now go to the reaction. Okay, so one famous reaction is this. I think you should have known it. HVZ reaction, Hell-Volhard-Zelensky reaction, right? It's pretty simple. If I have CH3COOH, if I go for what is it? HCl or HX in the presence of red phosphorus. Mechanism is not important. What you have to understand is one alpha hydrogen is removed, and I'm going to put the halogen there. So you will be getting CH2X-COOH, right? So that is my HVZ reaction. Okay. And then yeah, obviously salt formation. I told you, right? It is an acid. Obviously, it is going to react with NaOH. It is going to react with Na, and it is also going to react with a weak base such as Na2CO3, right? But phenols will be able to react with Na and NaOH, but not with Na2CO3. But carboxylic acids can react with weak bases also, like Na2CO3 and NaHCO3, right? That is also possible. And we know how to decide the acidic strengths. Okay, right. Okay, so that's it. That's about the normal reactions. Obviously, reduction reaction, right? So if I use strong reducing agent, I'll be ending up with alcohols, and if I use weak reducing agent, I'll be ending up with aldehydes. Okay. Now, especially there is a one thing you have to know. If you have, for example, CH3COOH, and if you want to just stop this reaction with aldehyde, there is only very few of the reducing agents are available, and one thing is dival-H. You have to remember this. Okay, dival-H is diisobutyl aluminium hydride. Okay, diisobutyl aluminium hydride. Structure is not important. I think you should have seen this in your NCRT also, right? Very simple. Like, but if at all you use any other thing, any other reducing agent, you will eventually end up only with alcohol, not aldehyde. Okay, right. Now, next thing is conversion of acid to its acid derivative. What and all you can do. Okay, conversion of this thing to acid derivative. Okay, now please understand, you we will be seeing everything together. Basically, I will see acid to acid derivatives, right? And I'll see one acid derivative to another. Right, now both are going to have similar mechanisms. Okay, now if you ask me what is the mechanism, right, if you ask me what is the mechanism, it is addition, elimination. Okay, I would say it is nucleophilic addition and elimination reaction. Both things are going to happen together, right? Say if you ask me how, right, maybe, okay, fine. So for example, you have CH3, C double bond O, OH, and say you go for C2H5OH, and I know I'm going to form ester. Acid plus alcohol will give me ester, right? So what is going to happen here, guys? I have the nucleophile here to be C2H5O minus. Okay, now this C2H5O minus will come and attack here, right? Okay, and obviously this bond will break. So what will you have? Before that, actually, you should have, fine, no issues. So you'll have CH3, CO, oh wait, CO minus. Now you have O, C2H5 and OH. Right, now what is going to happen? Now this bond will come back and the OH minus leaves. So you will be ending up with CH3, C double bond O, OC2H5. Very simple. So first is the addition of the nucleophile, break the double bond, make O minus, and then this bond is going to come back, eliminate OH minus to form C2H5, sorry, CH3CO, CO, C2H5. Right? This is the mechanism for all of the reactions which you're going to see. First, the nucleophile attacks, breaks the bond, the double bond comes back, OH minus or any other nucleophile which is there is going to leave. Okay, so that is what is the mechanism: addition, elimination. Okay, fine. So we will see how the one by one how we are going to do it. Right? Say first, acid to acid chlorides. Right now, generally, right, I can convert acid to acid chlorides, or I can convert directly acids to your esters. Other things are little difficult. Okay, converting into amide, converting into what is that, anhydride, right? All these things will be a little difficult, right? So what we'll do is that generally, if you want to convert acid to any other acid derivative other than acid chloride and your ester, it's always preferable to do the acid chloride first, to convert the acid into acid chloride, and then do whatever you want. Let me tell you why. I'll tell you. Okay, wait. So first, how do you convert this? Say if I have RCOOH, right, and you have to do any chlorinating agent. You know, so many chlorinating agents: PCl5, PCl3, SOCl2, right? All of these three will work. Now I'll form RCOCl. That's it. This is a very easy way. These are very good chlorinating agents. Okay, and the reaction is pretty efficient. You will end up with acid chlorides, and if you put alcohols, you'll end up with esters. Okay, now why is it that it is preferred that if I want to convert acid to any other acid derivative other than these two, why is it that I prefer this? It's because my halogen is a very good leaving group. Remember, nucleophilic substitution, right? My halogen is going to be a very good leaving group. Okay, and that's the reason why first I'll convert the acid to acid chloride, and then I do reaction whatever, how much ever you want, whatever you want. Okay, right, fine. So these two are the reactions possible for acid to acid derivatives. One for acid chloride, another is for esters.
Sir,
Okay.
so if
if
RCOOCl is formed,
RCOCl,
and if you want the Cl to be replaced by OH, you can directly do aqueous KOH, sir.
Yeah, if you just no, you don't have to do any hydrolysis. Not only with this, any acid derivative on hydrolysis will give me acid back.
Sir, so if you want to replace the Cl, any nucleophilic substitution is fine.
If you want to convert to what?
No, if you want to replace the Cl with something else, sir.
I'll tell you. So if you first thing, if you want to convert acid chloride or any other acid derivative back to acid, just go for hydrolysis. I will tell you how to convert to other things. Wait, I'm going for that one.
Okay, sir. Okay, sir.
Okay, right, fine. So that's about that, right? Okay, so now I have the acid chloride with me, right? Now, for example, if you put ammonia, now ammonia will be the nucleophile. Now what will happen? Same thing, addition, elimination. Ammonia will attack, this bond will break. So you'll form RCO minus, NH3 plus, Cl. Now this bond will go, this Cl minus will go back. So you'll form RCO, NH3 plus. Obviously, I have to remove the H plus to form RCO, NH2. Done. Right? So if you want to convert acid chloride to, this is a primary amide. Right? Hope you understand. Primary amine. How you have primary amine will have NH2. Same way primary amide will also have NH2. Okay. So if you want to convert acid chloride to a primary amide, right, you have to go for ammonia. Right? Now tell me, if at all I want to form a secondary amide, what will I put here instead of ammonia? If I want to convert RCOCl to, say I have R, C double bond O, NH, R dash. This is my secondary amide. What I have to put here? Tell me.
RNH2.
That's it. Use a primary amine. R dash NH2. Instead of ammonia, you go for R dash NH2. You'll end up with a secondary amide. Same way, if you put a secondary amine, here you'll be getting a tertiary amide. So you'll have RCO, N, R dash, R double dash. This is my tertiary amide. Okay, so that's about converting acid chlorides to amides, primary, secondary, and tertiary amides. Right. Okay. Now, next thing what you can see is obviously you can convert acid chlorides to. Okay, fine. If you have taken this down, I'll rub this part. Okay. Right. Say now if I have an acid chloride, right? Say I want to convert it to ester. Same thing you'll do. You'll just put an R dash OH. Alcohol you use exactly how you do for your acid to ester. You had an alcohol, same thing you'll do. So you'll end up with RCOO, RCO, OR dash. Right? Very simple. Now say if you want to convert it into an or is it anhydride, right? If you want to convert it into an anhydride, the nucleophile should be chosen accordingly. So I can use say R dash COO minus Na plus, salt of an acid I can use. I'll just make an acid react with sodium or NaOH or Na2CO3 and I'll be able to get this, right? Now RCOO minus will be the nucleophile attacking, right? So you will end up with RCO O C double bond O R dash. This is my anhydride. Okay, and this would have been my ester. Okay, now how will you form cyanides? I told you how do you form cyanides. You form the amide and you go for dehydration. You'll end up with cyanides. Okay, now the question is, okay, I'm able to convert acid chlorides to everything, right? But definitely what you have to understand is, people, I can convert some other anhydride to, I mean, some other acid derivative to another acid derivative also, right? Now what we have to understand is, if I know what is the reactivity, of this particular species, then I will tell that okay, from acid chloride I'm able to convert to say acid anhydride, right? But if I have to convert an amide to an acid anhydride, it's not possible, right? So let me tell you that. Like what I'm trying to tell you is an acid chloride, say to for example the acid anhydride is possible, right? This is okay, right? But if I have say an RCONH2 to this, it is not possible. Okay, now we have to understand why, right? Now the thing is, guys, it's all about the leaving groups. Maybe the nucleophile will attack, no issues. Maybe if I put one NH2 here, the nucleophile will attack this carbon, no issues, right? But will I be able to, oh wait, yeah, will I be able to remove that is the question, right? So what you have to understand, I will give you the reactivity, and accordingly you will be able to get the answer. Okay, just give me a moment. Okay, so the maximum reactive of all is your acid chlorides, right? Then comes your acid anhydrides are COO or R dash. So next is your esters, I guess. No, I think ester should have been before. No, it's not given here. Let me check. It should be. Okay, so first would be next after that acid anhydrides, right? Then comes esters, and at last would be amides, right? So what I can understand is I will be able to go this side of conversion, like I'll be able to convert like this, but opposite is not possible. This is not possible. Any of this, say this to this is not possible. This to this is not possible. Okay, so please understand that acid chlorides can be converted to any of these. Acid anhydrides can be converted to esters and amides, and esters can be converted to amides, and amides cannot be converted to anything, any other acid derivative. That's what you need to understand. Okay, it is all going to depend upon the leaving capacity, and some other factors are there, like electronic factors as well as your leaving capacity, right? So that means this side conversion is possible, but that side conversion is not possible. That's what you need to understand. Okay, so that, and then there is one more special reaction for esters. Let me tell you that. So that is called trans-esterification. Right, now trans-esterification, first I need to have an ester. Right, now if I put another alcohol, now you will replace R dash O minus with R double dash O minus. So you'll be ending up with OR double dash. This is what is called as trans-esterification. But there are certain conditions. What is the condition is the R dash double dash OH molecular mass should be greater than R dash OH molecular mass. Only then this reaction is possible. For example, if this was OCH3, right, I should at least use C2H5OH. Only then this reaction is possible, or else it is not possible. Mechanism is same. No, don't worry about that. Okay, so that is about trans-esterification. Now next, I forgot one important reaction, and that would be decarboxylation. Okay, decarboxylation. So you must have studied this in your this thing itself, your NCERT itself. Right. So if I have RCOOH, now there are various methods of decarboxylation. Say first one is what is my Kolb's method. Right. So in this, it's very simple. I use the salt of an acid, RCOONA, right? Then I go for some passing electricity, right? You will be ending up with R, 2 moles of this. Now, how this reaction happens is very simple. How am I getting this R and R getting doubled? Is very simple. Please understand, I have RCOO minus. Okay, now this bond comes here and this bond breaks. Right, so now you understand that it is going to be a homolytic cleavage or heterolytic cleavage, right? Say I will form, say, R dot, right? Another reaction will form R dot, another R dot will come. Now they both will come together to form RR. Okay, now either you can understand that it is going to be a free radical, or some other mechanism that it is going to be a carb anion also it is getting formed. All right, this is not this way actually. This is going to be this way. Okay, right? So either you can understand that it is going to be a carbon anion which is getting formed, or it is going to be a free radical which is getting formed. Either way, you will be getting the same product, RR. So if you have CH3COONA, you will be ending up with CH3CH3. Okay, now that is about decarboxylation. I have still other methods. Okay, so that be using CaO right? So if I have RCOONA, if I react it with CaO and heat it, I will be ending up with RH. If at all you don't want to double it, you just want whatever is there should be there, and you can directly go for Na to CO3. Okay, right? And if you have acid derivatives, or if you have calcium salt of an acid, say if you have, you hope you remember how the calcium salt of an acid will look. You will have R C double bond O, O, or it's like RCOO twice Ca, isn't it? Now what you have to understand is, if I heat it, right? If I heat it, we'll see what is going to happen. Right? So if I heat it, I will be eliminating CaCO3. Okay, if I'll be eliminating CaCO3. So if I write it properly, right? So CaC, now you have one Ca, say one carbon, 1, 2, 3 oxygen, CaCO3. Okay, I'm sorry, okay. Now if you eliminate it, if I remove CaCO3, what is remaining? R, and CO. So basically I'm going to form RCOR, and ketone can be formed out of a product if I use my salt of calcium acid, sorry, calcium salt of the acid. Okay, right? So RCO twice Ca. Remember that you are going to remove CaCO3 out. So let's write the structure. Remove 3 oxygen along with carbon. You will be ending up with RCOR. Okay, now that is about this. And anything else which I yeah, that is it. That's about decarboxylation. What's the time? Okay, fine. So that is about all the reactions possible for carboxylic acids. Okay, right. So we just have only amines left. Okay, maybe we'll take up amines next class. We'll do some problems. Okay, so let me bring 1 second. Okay. Right. So they want this compound to be synthesized. Okay, I want this compound to be formed, right? Now they're asking which of the following reactions will produce this. So they have given on H2SO4, option B, CH3 thrice C, CH double bond CH2, H2SO4 and water, and C, same compound with BH3 H2O2 in the presence of OH minus, or same compound with, I have CH3 COO twice Hg and NaBH4, right? So what any of these four is going to give me this product. What will be that product?
B.
Okay, so B, we'll see how it happens. We'll check for B. So first, if I check, obviously H plus will attack this one, the carbocation will form, it will be a secondary carbocation, and then I think methyl shift will happen. Yes. One second. No. See, if this happens, if I put H2SO4 bar this, you will be forming a carbocation here. Correct? Right. So obviously
Yes,
now
sir.
this is a secondary carbocation, so methyl shift can happen. So you look at the product, there is no methyl group here. This is CH3 that will eventually form. The H plus will attack here. So B cannot be the answer because it will undergo rearrangement.
Oh,
Understood? Right? The CH3 methyl shift will happen if you form the carbocation. Okay. Any other answers? What is this reaction? Option D. What is the name of the reaction? And it's not a name reaction, but still it has a name. What is this? I use mercury. What is this?
Oxymercuration.
Exactly. It is oxymercuration, demercuration. Right. So please understand, people, there are three ways by which you will be able to convert an alkene into an alcohol. One is acid catalyzed hydration, this one. Another one is this hydroboration oxidation. And the third one is oxymercuration, demercuration. Right. Now, please understand, I told you, when you want to do this, when you go for acid catalyzed hydration, you can form Markovnikov's product, but you'll always get rearrangement if there is a possibility for that. In this case, if you go, you will get anti-Markovnikov's product and obviously no rearrangement. And if you go for oxymercuration, demercuration, you will be getting Markovnikov's product and there is no chance for rearrangement. Right? So obviously you see this is a Markovnikov's product. OH is getting added to this carbon, but I should not undergo any rearrangement. So obviously option D will be the answer to this question. Everybody understood why this is the answer? You should have taken this down. I don't know whether you took it down. I told you oxymercuration, demercuration will, it's like addition of water molecule. Markovnikov's rule is followed, but no rearrangement. Okay, so option D would have been the answer to this question. Right? Okay. Next question. It's all about acidic strengths. Okay, this seems like a question. Right. Okay. So I have OH. This is benzene, and I have one OH. I have H. So I go for NaOH, 1 mole, right? And the next step is I go for CH3I, methyl iodide. What will be the product? Guess the product. Okay, maybe if I can add the stereochemistry also. Okay, first is NaOH, then reacting with CH3I. Two reactions. Right. So first tell me guys, I have this OH and this OH, and if I put a base, which OH will react? Either, I mean, the aliphatic OH or the phenolic OH?
Phenolic OH.
Yes, definitely. Whichever is more acidic, that's what will react. And obviously, I know other compared to aliphatic alcohols, phenols are more reactive, more acidic, sorry, more acidic in nature. Right. So after the first step, you would have formed O, Na, O minus, Na plus, and this would have been exactly as such. There is no change in this. Okay. Now, obviously, what is there? Now, if I go for CH3I, what reaction do you expect to happen?
Sir, that Na will go.
Okay, Na will go. Okay, then?
I will be substituted, sir.
That's a nucleophilic substitution reaction, right?
Okay.
So basically, this O minus will attack this carbon, and this I would be eliminated, right? So if you look at what is the product would have been O CH3, and this would have stayed as such. That's it. There is no change in that, right? So this stereochemistry and all is just given to confuse you, right? What you have to understand is obviously phenols are more acidic, though NaOH will react with that only. Okay, fine, cool. That is the reaction. I mean, that is the answer. Okay, let's see any other. Okay. Say predict the product.
Sir, it's Markovnikov product, sir.
Yeah, but you cannot stop with that. Right? Say now, if you tell I will get Br here, and this is the product. This option is there, but this is wrong. It is not going to stop here. Now, this is an example for intramolecular nucleophilic substitution, right? So you have a better nucleophile and you have a good leaving group. So obviously, this will come and attack here, and the Br minus leaves. That will be the last product. So you'll see how many membered ring is formed. 1, 2, 3, 4, 5, 6. A 6-membered ring along with oxygen. Okay, a 6-membered ring along with oxygen. And the carbon atom next to the oxygen atom, this side, is having 2 methyl groups. Carbon atom next to the oxygen atom, I mean oxygen atom, this carbon atom is having 2 methyl groups, right? Same way, this carbon atom, that is, okay, the oxygen atoms is next carbon atom. Oxygen atoms is next carbon atom. This side is again having a methyl group. So one CH3, another CH3, another CH3. Anybody got this answer? We have already done some questions like this. I've already given you, like when you have a good leaving group and a good nucleophile in the same compound, it will always undergo intramolecular nucleophilic substitution. Okay, so please be very careful with this. Right, next question. Okay, please take this down. We'll go for the next question. Okay. Right. So I have okay. So first is this, second is this. Right. See, I'm just making you scared. If you don't get scared and just look at it properly, you know the answer to this question. Can you tell me what is this group?
Docile.
Ah, right. It is docile group, toluene sulfonyl group, and obviously in this case it is going to be toluene sulfonyl chloride. Right? Why is it? What is it used for?
It's a better leaving group.
Okay, better leaving group. So if it reacts with alcohol, what will happen?
It will form ROTS.
Correct. Right. So basically H plus and Cl minus will be removed. So you'll form OTS. Okay. And as you told, it is going to be a good leaving group. So what is this is going? What is this going to do? This one. That is going to act as a
Nucleophile.
That's it. Now get me the answer. Okay. So if you would have got this answer, and okay, fine, we'll talk about that. So we'll have C triple bond C, with one CH3. This you would have got. And tell me, what will happen to the CH3? Is it going to be just like that, or is there going to be any change?
Inversion of configuration.
Absolutely, because it is going to be an SN2 mechanism. Correct, right? So obviously this, if I write it properly, okay, fine, no issues, right? This will become like this. This would have been the answer. Okay, why? Because you see, this is the carbon atom which is undergoing the nucleophilic substitution, this carbon, right? So definitely in that carbon, I should have inversion of configuration happening. Okay, so that's why you have CH3 pointing the other side. Okay, actually we should not be writing the compound like this, but still this they have mentioned, so definitely at least that you should change. Okay, so it has to undergo inversion, because both, again, both the options are there. You have to be very, very careful, right? Okay, so that's about that. Okay, this is the last question for the day. PR2 bar heating. Then I go for C2H5ONA in the presence of C2H5OH. Then I go for B2. Okay, I'll put it at the top. Next is B2H6 in the presence of H2O2, bar OH minus. And after that, I go for CrO3 in the presence of H2SO4. Remember, CrO3 bar H2SO4 is what is your Jones reagent. Okay, get the product. So 1, 2, 3, 4 reactions are going to happen.
Sir, in the previous question, why was an alkyne formed?
Why was an
Alkyne.
alkane formed?
Yes.
It is given in the question itself. They are given an alkene, right? They have given this given. It is given in the question. So this is the one who is going to act as a nucleophile. That is why I have to form alkene. There is no other reaction by which I'll be forming.
Okay, sir. I thought it was a double bond. Yes.
No. This is C triple bond.
Oh, okay.
Okay. Can I give the answer?
So 1 second, sir. Done, sir.
Okay, fine. So this is my free radical substitution, Br2 in the presence of light or heat, right? And please understand that it is going to undergo free radical mechanism. So I must form the most stable free radical, and in this case, it is going to be a tertiary free radical. So if I put Br2 in the presence of heat, you will be getting a compound like this. Yes, this will be the first step. Tertiary radical can be only formed here only. There's no other way. Okay, next. Now this C2H5ONA in the presence of C2H5OH, if I have just given you C2H5ONA, then you would have gone for nucleophilic substitution. Or now what you have to understand is after that you see there is a B2H6, the hydroboration oxidation. So definitely this is going to act as a base. Elimination reaction is going to happen. Yes, correct.
Alkene is formed.
Right, alkene will be formed. So this with RONA, whatever it is, RO minus Na plus, in the presence of ROH, again, I'm going to form Markovnikov's product. Oh, sorry, sides of product for sure. So you will form this. Okay, right. And then what I did, and then I go for hydroboration. Right now, that will form anti-Markovnikov's alcohol. So this will be the product. Okay, at last I go for CrO3 in the H2SO4 is going to be an oxidizing agent. So this will get converted to a double bond O. That's it. This will be the final product. How many of you got this?
Sir, I got it, sir.
Good.
I got it.
Good. Right. So yeah. So now we are getting more and more familiar with the reactions. We will get more and more familiar. Don't worry. So next class, that will be tomorrow. I'll be taking very less time for your finishing your amines because very less reactions are there. And then we'll tomorrow's class, say next 1 hour, and after that one more class, we'll be concentrating on the problem solving. Okay. So that would be it for today. And then we'll go for your physical chemistry, and then we'll be finishing maybe a 1-1-1-1 class if I can keep. So the deadline we gave for was 15th or 16th, right? That was the deadline. We will be able to complete it.
Sir,
Okay.
after that, can you do coordination chemistry, isomerism? Sir?
Yeah.
It's
Coordination
not
compounds, we'll
coordination,
concentrate on two things. One is isomerism, other will be crystal field theory. Both things I'll
yes, sir,
take.
because isomerism is not there in our portion in CBSE, so I'm not familiar with the concepts.
No issues. But again, JEE point of view, isomerism is not important that much, but still we will touch it. And then the most important, the only, if at all they're going to ask questions from your coordination compounds, it is going to be from crystal field theory. Okay, so that will spend some good amount of time.
Sir, can you also explain IUPAC naming very quickly, sir, for that?
Yeah, that is fine. IUPAC naming will be easy only. That will be okay. Right.
Yes.
And then anything else? Yeah, we'll be able to do it. And then how many have started writing tests? Did you already start taking the test series? Mock tests?
No, sir. Revision exams are going.
I told you that was not important. Right. Anyways, please start it as soon as possible. Right. As I told you, the number of tests is proportional to your marks. Right. Keep that in mind. How much ever I teach you, how much ever I bang my head, you bang your head. For understanding, not going to help. Mock test, yes, it will help. Right. Fine. Anyways, thank you so much, people. We'll meet again tomorrow.
Thank you, sir.
Yeah.
Thank you.
Thank you, sir.
You.